Lake Tahoe has just surged to 6,229 feet, its absolute maximum capacity, every single drop of water the law allows, and the lake is pressing against that limit right now, with nowhere left to go. After 5 years of brutal drought, billions of gallons flooded back almost overnight. The headlines called it a miracle, a comeback story. California's water crisis finally over. But beneath that beautiful, crystal-clear surface, something is waking up. Hidden under the lake bed runs one of the most dangerous fault lines in America. A 25-mile crack in the earth that scientists say is 4,000 years overdue for a catastrophic rupture. And right now, billions of tons of water are pressing down on it, pushing on it every second of every day. The seismographs around the lake are already responding. Small tremors are increasing. Scientists are watching the instruments around the clock. Because if that fault snaps while the lake sits at maximum capacity, the earthquake will not even be the worst part. So here is the question nobody on that shoreline is asking, but every seismologist studying this region is. Is the water that saved California from drought the very thing that finally wakes up the fault beneath it? 5 years ago, Lake Tahoe was dying. The drought had been relentless. Month after month, the water level dropped lower and lower, exposing a shoreline no one had seen in generations. Ancient tree stumps that had been submerged for decades re-emerged like ghosts from another century. Boat ramps that once extended directly into deep blue water ended abruptly in dry air, stranded dozens of feet from the receding edge. Marina owners watched reservations disappear and revenue collapse. Residents whispered about whether they were witnessing a permanent shift, not a temporary cycle. Climate scientists warned that California's megadrought could fundamentally reshape the West. Some even questioned whether the lake might ever fully recover. Then came the atmospheric rivers. Beginning in late 2022, massive storm systems barreled into the Sierra Nevada with extraordinary force. Week after week, they delivered torrents of rain at lower elevations and historic snowfall in the mountains. Snow accumulated so rapidly that even seasoned meteorologists were stunned. Monitoring stations reported snowpack levels reaching 237% of normal, nearly 2.5 times what the range typically holds. The Sierra Nevada had transformed into a colossal frozen reservoir, quietly storing billions of gallons of water high above the Tahoe Basin. When spring arrived, the melt was explosive. Warmer temperatures unlocked that frozen storage all at once. Water surged down creeks and tributaries into Lake Tahoe faster than hydrologists had projected and faster than water managers had prepared for. The lake rose 4 feet in a single season, an astonishing reversal after years of decline. Officials scrambled to respond, opening dam gates at the Truckee River outlet to release maximum legal flows downstream. Engineers monitored inflow and outflow rates around the clock, attempting to prevent flooding while preserving the lake's delicate balance. But the surge continued. By early 2024, Lake Tahoe reached levels not seen since 2019 and kept climbing toward its legally defined maximum. Beaches that had been cracked and dusty just 2 years earlier were once again submerged beneath clear alpine water. Kayakers returned. Swimmers filled the shallows. Marina slips were full. Tourism officials celebrated what many called a hydrological miracle. Headlines declared the drought defeated. The lake had come back. Yet beneath the optimism, something more subtle was unfolding. Scientists monitoring the region began detecting anomalies unrelated to water clarity or elevation. Seismographs positioned around the Tahoe Basin recorded a noticeable increase in microtremors, small, almost imperceptible shifts in the earth. The readings were not dramatic enough to alarm the public, but the patterns were consistent, quiet, persistent, difficult to dismiss. The lake had returned, but the immense weight of billions of gallons of newly restored water was pressing down on ancient faults beneath the basin, and the earth was beginning to respond. Beneath the surface of Lake Tahoe lies a geological secret few visitors ever imagine. Running directly under the lake bed for approximately 25 miles is a massive fracture known as the West Tahoe Fault. Scientists have studied it for decades. It has been mapped, measured, and analyzed in detail by researchers from the University of Nevada, Reno, and the United States Geological Survey. What they have uncovered is deeply unsettling. The West Tahoe Fault is capable of generating earthquakes as powerful as magnitude 7.3. To understand what that means, consider a comparison. The devastating 1989 Loma Prieta earthquake measured 6.9. That event collapsed freeway structures, destroyed homes, and killed 63 people across the San Francisco Bay Area. A magnitude 7.3 earthquake would release roughly 2.5 times more energy. The increase is not linear. Each decimal jump represents a dramatic leap in destructive force. A 7.3 would not simply be slightly worse. It would be categorically more powerful. Yet magnitude alone is not what troubles geologists most. It is the timeline. Sediment cores pulled from the lake floor reveal evidence of ancient ruptures. Underwater fault scarps, steep steps in the lakebed formed by past earthquakes, trace the fault's violent history. By analyzing layers of displaced sediment, scientists determined the last major rupture occurred approximately 4,000 years ago. Based on measured slip rates and accumulated strain, researchers believe the fault may be approaching the end of its seismic cycle. In simple terms, pressure has been building for 4 millennia. The West Tahoe Fault is not a single clean crack. It is a complex system of interconnected segments running along the western edge of the basin. If one segment fails, others could rupture in sequence, creating a cascading event. Some models suggest it could even interact with nearby faults within the Sierra Nevada region, amplifying the overall impact. And yet, despite this risk, the fault receives only a fraction of the public attention given to California's more famous systems. There are no blockbuster films about it. No warning signs greet tourists stepping onto the shoreline. Swimmers glide across the surface, unaware that an active fault lies directly beneath them. Seismologists consistently rank the Tahoe Basin among California's higher-risk regions for large earthquakes. Now add one more variable: billions of tons of water sitting directly above an overdue fault. That immense weight increases stress on the crust below. When rock that has been locked for thousands of years finally gives way, the release will be sudden, violent, and unstoppable. The surface may appear calm, but deep below, the clock is still ticking. Most people never think about how heavy water actually is. A single cubic foot of water weighs 62 pounds. That is heavier than most people can comfortably carry. Now multiply that weight by the 39 trillion gallons that Lake Tahoe holds at maximum capacity. The math produces a number so large it stops feeling real. But the weight is real. Billions of tons pressing down on the lakebed every single second of every single day. And that weight does not simply rest on solid ground. It pushes into fractured bedrock. It forces its way into cracks and fissures deep in the geological structure below the lake. When that kind of pressure sits directly above an active fault system, it creates conditions that seismologists have documented triggering earthquakes all over the world. The phenomenon has a name: induced seismicity. Large bodies of water can cause earthquakes. This is not a theory. It is documented, verified, historical fact. In 1967, India's Koyna Dam reservoir triggered a magnitude 6.3 earthquake that killed 180 people. Lake Mead behind Hoover Dam has generated hundreds of small earthquakes since it filled in the 1930s. China's Zhaipingpu Reservoir may have contributed to the catastrophic 2008 Sichuan earthquake that killed nearly 70,000 people. Scientists continue debating the exact connection in that final case, but the broader pattern is undeniable.
Water can trigger earthquakes through two mechanisms. The immense vertical weight increases pressure on fault systems that are already under horizontal tectonic stress. But the more dangerous effect occurs underground, hidden from view. Water seeps into cracks within the rock and raises what geologists refer to as pore pressure. That pressure decreases the friction that normally keeps fault surfaces locked in place. In simple terms, water lubricates the fault plane. It allows the built-up strain to release suddenly and violently. Now apply this directly to Lake Tahoe. Maximum capacity, maximum load, maximum pressure. All of it pushing down on the West Tahoe Fault, which has already been storing strain for 4,000 years without releasing it. The fault was already overdue. Now billions of extra tons are bearing down on it.
The elements are aligning, and the instruments are detecting exactly what scientists feared. Inside the monitoring stations scattered around the Tahoe Basin, seismographs trace their endless lines across digital screens. Every tremor registers. Every subtle shift in the Earth's crust leaves its signature in the data. Scientists watch these readings with the patience of hunters waiting for something they know will eventually appear. And lately, the readings have been changing. Recent monitoring from stations positioned around the basin reveals a disturbing pattern. Small earthquakes are increasing in frequency along the West Tahoe Fault system. Magnitude 1.9 tremors have been detected in recent months. These quakes are too small for any human to feel. You could be standing directly above one and never know it happened. But the instruments feel everything, and the instruments are not lying. Seismologists call these events micro-seismic activity. To most people, a magnitude 1.9 earthquake sounds completely harmless. Barely a whisper in the geological record. But earthquake scientists recognize these small tremors for what they might represent. Potential precursors. Warning shots from a fault system under increasing stress. The geological equivalent of a structure groaning before it collapses. The historical record supports that concern. Before major earthquakes, fault systems often exhibit increased microseismic activity. Small ruptures along fault segments release tiny amounts of accumulated strain. These events can signal that larger sections of the fault are approaching their breaking point. The 2011 Tahoe earthquake that devastated Japan and triggered a catastrophic tsunami was preceded by an increase in smaller quakes. The pattern has repeated before major ruptures across the world. Monitoring stations around Lake Tahoe now operate around the clock. University researchers and USGS scientists analyze every tremor, mapping locations and measuring depths, tracking the frequency of events week by week. The baseline is shifting. Activity levels that appeared normal 5 years ago now look elevated against the backdrop of maximum water pressure bearing down on the fault below. The honest scientific answer is that nobody can say for certain what these tremors mean. They might signal an imminent major rupture. They might slowly release enough strain to delay one. Or they might mean nothing at all. What scientists will say is this: the combination of factors present at Lake Tahoe right now is not something anyone is willing to dismiss. If the West Tahoe Fault ruptures while the lake sits at maximum capacity, the earthquake will only be the beginning. What follows could be far worse. Lake Tahoe has underwater terrain that is not a gentle slope that gradually descends toward a flat bottom. The lake plunges to depths exceeding 1,600 feet, with near vertical walls dropping away in some areas. Massive underwater slopes of loose sediment cling to these steep gradients, held in place by nothing more than friction and geological patience. A magnitude 7.3 earthquake would shake these formations with violent, sudden force. The sediment would not hold. Scientists believe the result would be catastrophic underwater landslides, millions of tons of material collapsing into the lake's depths simultaneously in a matter of seconds. When that much mass displaces that much water that quickly, it generates a tsunami. This is not speculation. Geological evidence confirms it has happened before. Researchers studying the lakebed have identified massive underwater landslide deposits from prehistoric events preserved in the sediment record. The McKinney Bay landslide moved approximately 12 cubic miles of material in a single ancient catastrophe. The wave it generated would have been devastating to anything standing on those shores. Modern modeling projects what a similar event would produce today. Waves potentially reaching 30 feet or higher, traveling across the lake at speeds approaching 100 miles per hour. Shoreline communities would have almost no warning. The geography that makes Lake Tahoe one of the most beautiful places in America also makes it one of the most dangerous in this scenario. The lake is only 12 miles wide at its broadest point. A tsunami generated on one side reaches the opposite shore within minutes. Ocean tsunamis give coastal populations hours to evacuate. Warning systems detect distant earthquakes and issue alerts long before waves arrive. Lake Tahoe offers no such time. The earthquake and the tsunami would arrive almost simultaneously. Residents would feel the ground shaking and see the water rising within the same terrible minutes. And then it gets worse. The enclosed basin means waves reflect off surrounding shorelines, bouncing back and forth across the water, striking communities multiple times. The first wave is only the first assault. South Lake Tahoe, Tahoe City, Incline Village, Kings Beach, State Line. These are not just names on a map. They are communities, families, homes built along one of America's most spectacular shorelines. Restaurants, resorts, marinas, and neighborhoods that have grown up around the assumption that the beautiful water beside them is nothing but a gift. Most of the people living and vacationing there have never heard of the West Tahoe Fault. Most never will. Approximately 55,000 people call the Lake Tahoe Basin home year-round. But that number is just the beginning. Summer weekends push over 100,000 visitors onto the shoreline. Ski season fills Nevada casinos and California resorts with thousands more. On any given holiday weekend, the population surrounding the lake can triple. All of those people compressed into a mountain basin accessible by a handful of narrow two-lane highways. During normal summer traffic, those roads already jam with vacationers moving at a crawl. During a mass evacuation with minutes on the clock, they would become parking lots. The jurisdictional reality makes it worse. Lake Tahoe straddles the border between California and Nevada.
5 counties share authority over the shoreline communities. 2 state governments, several fire districts, and numerous local agencies would all need to coordinate immediately during a crisis that develops faster than most emergency systems are built to handle. And the warning infrastructure simply isn't in place. Coastal communities facing the ocean have tsunami sirens. They have clearly marked evacuation routes. They run public awareness campaigns that explain exactly what residents should do and where they should go. Lake Tahoe has none of these measures. No sirens are installed along the shoreline. No tsunami evacuation zones have been created.
No public awareness campaigns explain what lurks beneath the surface of the water people are swimming in. Property values along the shoreline exceed $15 billion. Luxury homes, historic resorts, and commercial districts built on the quiet assumption that the lake is safe. Most residents moved here for the beauty, for the peace, for the escape. Few have any idea they built their lives directly above a fault that has been waiting 4,000 years to move. The technology monitoring Lake Tahoe has never been more advanced. Modern seismic networks detect earthquakes too small for any human to feel. GPS stations measure ground deformation down to millimeters. Satellite imagery tracks surface changes invisible to the naked eye. Researchers can monitor the West Tahoe Fault with a precision that previous generations of scientists could not have imagined. The instruments are sensitive, the data is constant, the coverage is comprehensive, and yet one fundamental limitation remains. Earthquakes cannot be predicted. Scientists can identify faults. They can calculate probability. They can recognize warning signs and measure accumulating strain. What they cannot do is tell you when. The Earth does not issue announcements. A fault can remain locked for centuries, past its average rupture interval. or it can fail tomorrow morning. The uncertainty is absolute, and it is unavoidable. No instrument built, no model designed, no algorithm developed has ever successfully predicted the moment a fault decides to move. The research continues regardless. University of Nevada seismologists analyze tremor patterns looking for anomalies that might sharpen the picture. USGS scientists refine hazard models as new data about the fault system emerges. Graduate students spend years examining sediment cores pulled from the lake bottom, studying prehistoric catastrophes preserved in ancient layers of rock and silt, trying to understand the rhythm of a fault that moves on timescales that dwarf human civilization. Funding remains a persistent obstacle. The West Tahoe fault generates no dramatic headlines. No ruptures in living memory keep it in public consciousness. Research dollars flow toward the San Andreas and other famous systems, while Tahoe's hidden threat receives a fraction of the attention scientists believe it deserves. But the expert consensus on one point is uncomfortable and unanimous. The fault will rupture, not might. Will. Faults that accumulate strain must eventually release it. This is not opinion or speculation, it is physics. The West Tahoe fault has been building pressure for 4,000 years. That pressure will find release. The only questions that remain are when and how violently. Until then, the scientists watch. The instruments record, and the lake keeps pressing down. Lake Tahoe looks exactly the way it always has. Crystal blue water stretches toward mountain horizons. Sunlight breaks across the surface in the early morning. Tourists arrive with cameras, kayaks, and coolers packed for a perfect summer day. Families spread towels on the sand. Children run into the water. Boats cut slow lines across the surface, while passengers lean back and decide that this, right here, might be the most beautiful place they have ever seen. They photograph the sunsets. They post the images. They tell their friends that Tahoe is paradise. They do not see what lies below. They do not know what is waiting. Beneath that postcard surface, 4,000 years of accumulated strain sits locked inside fractured bedrock that most of these visitors will never think about. The West Tahoe fault does not care about tourism revenue. It does not care about property values, holiday weekends, or the 55,000 people who have built their lives along its shores. It operates on geological time, patient beyond anything the human mind can genuinely comprehend, slow beyond measure, but not stopped, never stopped. The lake has reached 6,229 feet, maximum capacity. Billions of tons press down on ancient fractures with relentless, unceasing force. The atmospheric rivers delivered what California desperately needed, and headlines celebrated the miracle. But the water that refilled this lake did not simply restore what was lost. It added a new variable to a geological equation that was already dangerously unbalanced. Tremors continue registering on instruments that most people nearby will never see. Scientists continue watching data that most people nearby will never read. The emergency infrastructure gaps remain unfilled.
The warning systems are still not in place. The fault has not moved, continuing to build tension, continuing to wait, slowly pushing toward an outcome that no one can predict and no one can prevent. Somewhere beneath that incredibly blue water, in darkness, silence, and the slow pace of geological time, the pressure continues to rise. And the question every seismologist studying this region carries with them becomes harder to ignore with each passing day. Has the fault beneath America's most beautiful lake finally reached its breaking point as well?